Okay. The main object we'll work with is sum or product set AB, finite non-empty, sets A plus B is a set containing all the sums A plus B whenever A is in A, B in B is in B. Or similarly, we can define product set A times B, A in A, B in B, and A divide by B. In B, closer to the end of the course, we will work with such object, but not now. Okay. We naturally will learn size of the set. Do you understand the construction? Do you need examples? Okay. Probably A is 1, 2, 1, 2. B is 1, 3, 5. Oh, 7. Then A plus B is 1 plus 1 is 2, 1 plus 3 is 4, 1 plus 7 is 8, 2 plus 1 is 3, 2 plus 3 is 5, and 2 plus 7 is 9. But let's organize it this way. Then this would be A plus B1 is 2, 4, 6. 2 plus 1 is 3. Okay. A2, A1 is 1, 3. 3 plus 1 is 4, is in here. 3 plus 3 is 6, it's in here. 3 plus 5 is 8, it's new. So the sum set A1 plus B1 is this one. Well, this set has size 6. We add one set of size 2. Here, this set is size 3. We got the set size 6. Here, set cardinality 2, cardinality 3. We got the set cardinality 5. So, the size, the cardinality of some sets dramatically depends on configuration of sets, right? It depends on them. It could be different. And in this, to this context, we have two questions. First, we have to define the limits of changes of some sets. And second question, probably for some sizes, there are special structure of set having this particular sum set, right? First problem, estimate. First problems. estimate lower bound and upper bound. Find lower bound and upper bound for subset, for size of subset. Second problem, suppose we know that A plus B is some K. What can we say about AB? Well, this problem is called direct problem. This is called inverse problem. So, inverse in the sense we know information about size, we have to get information about structure. Probably for some sizes, there are no structure. When we don't have any structure, when a random set has this size, if we randomly generate two subsets, add them up, and in mean we get this size, then there are no structure, right? Because random sets, addition of random sets having the structure. But sometimes okay, we will learn basically our course will cover part of results of this, was both of these two questions. Well, okay, trivial bounds. Bounds for A plus B in abelian group. Some bounds working in non-abelian case. Some don't. Some of them don't. I just well, usually I work in abelian group, but this trivial bound, most of them works also in non-abelian case, because we actually don't use ability. That's the fact that group is abelian, right? First, A plus B is more equal. A plus B is more equal than cardinality of A, and it's at least cardinality of A, at most cardinality of, no, at least cardinality of A. It also at least cardinality of B. Both bounds could happen. So we will write this one, maximum between A and B. We prove both bounds. Small lower bound cardinality of A, lower bound cardinality of B. Upper bound is this one. Upper bound is this one. Okay, let's prove this. How to prove? Prove that cardinality of A plus B, is at least cardinality of A. How to show that? We can take what? Yeah, we can take, but well, naturally, A and B finite non-empty sets in here. So B, A, non-empty and finite. In other way, it's not that correctly defined notion of cardinality, right? For infinite sets. We can define cardinality for them, but operations work not this way in this setting. All right. Cardinality of A plus B at least A. How to show? Well, we must find inside A plus B cardinality of A elements, different elements. How to do that? Well, let's select any element B0 from B, and then B0 plus A. What side of the set? It's A, right? Contains cardinality of A elements, right? And all these elements are inside A plus B. So we found at least cardinality of elements inside A plus B. So A plus B is at least cardinality of A. Cardinality of A plus B is at least cardinality of A. So how to show that cardinality of A plus B is at least cardinality of B? With this. Okay, how to show this? For the same process, the fixed one element from A, and A0 plus B contains cardinality of B elements. So we have both bounds, so we have, this means we have these bounds, right? Upper bound, how to show this? Is at most A times B. How to show it? Well, we made an interpretation between the cardinality of A and B. This is like the maximum of the estimation of the area. Yeah, right. And that's kind of informal. How to show this more formally, in more formal way? Yeah, you're right. We just take all the possible sums. If they are disjoint, we have exactly A times B elements. If they are not, we have smaller than A times B elements. You got, right? Oh, Anthony here. You got it? Well, just we just say, write down all the elements. Write down all the elements of some set. This is A0 plus B0, A0 plus B1, and so on and so forth. We have to remove all the repetitions, right? So in this list, in this list. In this list, A times B element, but they could be same element, right? They could repeat. Well, so when we remove out from this list all the repetitions, we got the sum set, right? In this case, there were some repetitions, so we removed some sums here. In here, we didn't have any repetitions here in this set. So, informally, this is a proof, right? This is it. A maximum number of disjoint elements can be larger than number of elements in this list, right? This list contains A times B elements. Well, but can we make this proof more formal? How to make this proof more formal? All right. We just build a surjection between A times B and A plus B. If there are surjection between A times B and A plus B, this means that A times B is at least having at least the same number of elements as in A plus B, right? Otherwise, there are no surjection. So, how to build this surjection? What is F from A and B? A plus B. This is surjection onto A plus B. If there are surjection, this means that A plus B is at most A times B. Right? Well, second bound. Here is first, second bound. Right. A plus A is at least cardinality of A, but at most, guess what? In a abelian group. In a abelian group. At most, what number of this, what maximal number of distinct element in this list for A plus A in a abelian group? In a abelian group, A1 plus A2 equals A2 plus A1. There are trivial equalities, right? So we have to remove some elements automatically because they must repeat due to properties of the group, right? So, what the maximal number of the elements in the list? Number of combinations from A elements by 2 with repetitions, right? Combinations. What the number of combinations? 2 from 2 by 2 elements, the repetitions. You learned combinatorics, right? No, it's without repetitions, with repetitions. Repetitions appears when we have this element. A0 plus A0 is equal to A0 plus A0. It's binomial coefficient. A plus 1, choose 2, right? Combinations with repetition from A to from cardinality of A elements by 2. Do you understand? With repetition. With repetition. Well, so this follows from first, lower bound follows from first point, upper bound the same, we had proved the same way, but the cardinality of the least is smaller. And actually we can build a surjection, but not from A times A, but smaller sets. All the combinations, all the possible combinations, A and B, from all the sets of non-ordered pairs, A and B, right? The size of the set non-ordered pair is subset. I don't know any good common notation for this object. Probably there are, I don't know. Well, this object, we build the projection from this set to A plus A, and this proves this the same thing. Okay, but this works in abelian group only. In non-abelian case, we have A square, not better than A square, right? In non-abelian case, this not working. There are no equalities. A1 plus A2 equals to A2 plus A1. So we have A square. Right. And also we can just recurrently prove the same bound for K times sum. What the upper bound? Choose K from? No. Because we have to choose from by K, not by 2. Number of combinations from N. Number of combinations from N choose k with repetitions is n plus k minus 1 by k. Good. Okay. It's trivial ones. Trivial bounds. This work in any abelian group, but in some groups we can make better. Lower bound, I mean. We can, well, usually in arbitrary group, this is best possible bounds. But in some groups, we can make better. This bound is not attainable, and we usually have more elements in some sets. Well, okay, let's prove this one. Well, suppose a subset of whole numbers, group of whole numbers, in addition, I mean. There are multiplication, right? I mean addition here, group by addition. Well, a finite, non-empty subset. Then IB. Then A plus B is at least cardinality of A plus cardinality of B minus 1. Okay, let's prove it. Well, it's quite known bound. Probably you know how to prove it. Do you? Well, A, we can order elements of A. Well, just let's increase let's order number elements of A in increasing order, right? So A0 is smaller than A1, smaller than A2, smaller than AK minus 1. Elements, let's order elements of B also in increasing order. B0 smaller than B1, smaller than BL minus 1. Then we have to find at least this number elements inside A plus B. How to do it?
We can sum the first element of the element. That guarantees that it will be every element will be less than the other. And then we sum from k minus 1.
No. Look here. First we increase indices in B, then we stop when we reach maximal index, and we start increasing indices in A.
minus 1. Yeah.
In this chain, k plus L minus 1 elements, right? They are distinct because they are ordered in this way. So this proves this bound, right? Let's, well, upper bound for A plus B is A times B. It's quite an attainable bound. Well, probably it's good exercise how to build for any K and L two such sets such that A plus B in size is equally A times B. What about inverse question? Suppose we have A plus B, cardinality of A plus B equals to A plus B minus 1. What can we say about sets A and B? In whole numbers, this is quite natural question. All right, okay. I just say this, well, if A plus B equals to A times B, there are structure, but kind of weak structure. For two random sets, A plus B, for two random sets from minus n till n, if we choose two random subsets, we have A plus B in size close to A times B, close to, not equal, but close to. So for there are for upper bound, if size of A plus B close to upper bound, there are no structure. If it's exactly upper bound, then there are kind of weak structure. But for lower bound, very strong structure. Okay, this structure called arithmetic progressions. So theorem 2. First, we show that if they are equal in size, suppose A, B, subset of Z, finite and empty. Subsets of an abelian group, right? A cardinality of A equals to cardinality of B, cardinality equals to K. Then, and we know that cardinality of A plus B is equal to 2K plus 1. Right? Okay. Then.
1 or minus 1?
Minus. Then A plus B, A and B are arithmetic progressions. with the same difference. Okay. Proof. Well, what we know, we have two subsets, and we know the equal in size, and size of A plus B is 2k minus 1. That's all we know, right? Okay, let's write all the elements of A in increasing order. And all the elements of B in increasing order. Well, what we can do this way, this thing. We write down this chain. It ends with AK minus 1 plus BK minus 1. Do you understand that all this chain contains all the possible elements from A plus B? Because A plus B has size 2k minus 1, and in this chain 2k minus 1 different elements, distinct elements. So let's reorder the chain. Let's write down another chain. Look here. These elements are. This also chain of elements from A plus B. Moreover, these two chains have odd elements of this chain are the same. Even elements are different. What conclusion can we make from this? Yeah, elements in even positions are the same. So, all right. So, for any I from 0 till k minus 2, I guess AI plus BI plus 1 equals to AI plus 1 equal plus BI, right? So this means that AI plus 1 minus AI equals to BI plus 1 minus BI. This means that if A and B are arithmetic progressions, then they have same common difference. But this, we need more information. This is not sufficient, right? Okay. How can we obtain this additional information? Well, let's be.
We want to see there is an arithmetic progression.
The additional information there will have to show that at least A then, well, we have to show that A is at arithmetic progressions. From this, then follows that B also arithmetic progression, right? And progression with the same difference. How to show that A arithmetic progression? Well, let's build another chain. AI minus 1, strictly smaller than AI plus BI, strictly smaller than AI plus 1, AI BI plus 1, right? Yeah, that's correct. I goes from 1 till K minus 2, if I'm not mistaken. Right? What about second chain? AI minus 1 plus BI smaller than what? I minus 1, probably I minus 1, right? Well, in the same way, these are equal because both chains contain all elements from A plus B, and this part of chains are the same. So intermediate parts also are the same because there are no two different elements between these two elements. If we have to, this means we have two different representations of the same element, right? Okay. This means that AI plus BI equals to AI minus 1 plus BI plus 1. So the same, this is equivalent to BI plus 1 minus BI equals AI minus 1 minus AI. Oh, no. AI minus 1. Well, combining these two equalities, what we can get? If we combine these two guys. AI plus 1 minus AI equals to AI minus 1. So, though consecutive differences are the same, so this means that A is arithmetic progressions. The same we can conclude from about B, right? So these two equalities gives us the structure of arithmetic progressions with the same differences. With the same differences. Well, we show this for case of equal cardinalities. How to remove this how to remove this requirement. Round 3. Well, suppose that AB subset of Z, fine into an empty, subsets such that A plus B is cardinality of A plus cardinality of B minus 1. Then A and B are arithmetic progressions with the same with the same difference. With the same difference. Well, proof. Proof. How to spread this theorem? How to unify this theorem to this case? Well, again, suppose A is A0, A1, AK minus 1. Just write down all the elements of A in increasing order, and write down all the elements of B in increasing order. And suppose that K is smaller or equal than L. Cardinality of A what? Yeah, we're going to do the same thing, but well, if cardinalities are different, we're going to show this thing that we just cut down the fragment of consecutive elements from B of size cardinality of A, and show that this fragment is A and this fragment is arithmetic progressions, both arithmetic progressions with the same difference. And since we kind of arbitrary fragment, this means that B also arithmetic progressions will work this way, right? So we just take a frame of size K and cut down the segment of B of size K. Okay. Choose any t, this segment starts from t and has size t plus k till t plus k minus 1, right? Right? Well, this then we just cut off the segment of size k, right? T goes from 0 till what? T plus k minus 1 must be at most L minus 1, right? So T is at most L minus K. All right, and define this one, right, B0, it's BT0, because this part depends on T. So B is T0, it's part initial segment. B0 till B T minus 1. Right? Okay. B1T, it's second segment. It's this part, the main part, from BT till BT plus K minus 1. And third part, it's final segment. BT second. It's B T plus K till B L minus 1. Good? Okay. Look here. B0T is empty. B0T is empty. If T equals to 0. Because otherwise, well, these two conditions contradict to each other. T equals 0, there are no B minus 1. So, and also here, BT2 is empty if T equals to T equals to L minus K. So in border cases, in beginning, in with smaller meaning, in smallest meaning, in the largest meaning of T, some segments could be empty. Right. A plus B is what? what can we say about A plus B? Well, this is union of A plus B1, BT1, BT0, A plus BT1, and A plus BT2. Right? Let's estimate from above all these parts, sizes of these parts. Well, what is size of A plus BT0? Well, no. This is not working on this. Yeah, right. 1 minute, sorry. A0 here. We choose this unit, this is inside this. A0 from here, and in here we must what? Let's do this. AK minus 1, yeah, right. AK minus 1. Well, because it's hard to compute this size of A plus B, T0. So, A plus B, A0 plus BT, 0. Why we added these elements? Just because make sure that these parts are non-intersecting. Why they are non-intersecting? Why they are non-intersecting? Because A0 plus B, all the elements of BT are smaller than any elements in here, because all the elements from BT are larger than elements from BT0. So, and all the elements of A small at least A0, right? So all the elements from here strictly greater than all the elements from here. And all the elements from here is strictly greater than all the elements from here because of this AK plus 1 and the fact that all the elements from BT2 is larger than all the elements from BT1, right? So they are distinct because they are ordered this way, right? What the size of A0 plus BT0 is T. What the size of A plus BT1? We don't know, but we can say that it's at least 2K plus 1, right? Minus 1. Because of theorem 1. What is the size of AK plus 1 plus BT2? Well, T plus K plus j. Whenever j goes from 0 till, how we transform t plus k into L minus 1. J t plus k plus j equals L minus 1 whenever j equals to L minus 1, L minus t minus k minus 1, right? I think yes. Right. Well, what is this? Well, j from 0 till L minus t minus k minus 1. How many elements in here? L minus t minus k, right? So, a plus b, size of a plus b, is at least size of a0 plus bt1, bt0, plus size of a plus bt1, plus size of ak minus 1, plus bt2. Because all these parts are non-intersecting, and well, that's because of this. And this union contains inside a plus b. Okay, this is at least t plus 2k minus 1 plus L minus t minus k. Well, and we got L plus k minus 1. But also size of a plus b equals to k plus L minus 1, right? By condition of the theorem, right? It follows from condition of the theorem. A plus b equals to k, cardinality of a plus b equals to k plus L minus 1 because of this, because of that, because of condition of the theorem. This means that a plus bt1 is to k minus 1 cardinality of this. This means by theorem 2 that a and bt1 are arithmetic progressions with the same difference. Well, upper bound and lower bound are the same. This means we don't have inequalities here, we have equalities here. So this size is equal to k minus 1. So by theorem 2, a and b1, bt1 are arithmetic progressions with the same difference. But because we choose t in arbitrary way, right? We can say the same for a and b. Because well, all the segments of length k are arithmetic progressions, right? So we proved the theorem. Okay. Okay, good. The final theorem for today is this one. Theorem 4. Suppose A, B, subset of group G, finite, non-empty subsets of an abelian group G. In non-abelian case, this statement kind of works, but we cannot build the structure set in the same manner. There are difficulties with this point. Suppose also that A plus B is cardinality of A plus B is cardinality of A. Then, this is actually this is equivalent to what? In this case, lower bound, again, as I said, lower bound correspond to some strong structure, upper bound close to random. There are no structure for upper bound. Well, what kind of structure in here in any abelian group? Actually, subgroup. B is subset of some subgroup. There exists a finite subgroup H from G, such that as far as I remember this article, in a non-abelian case, there exists such subgroup, but not necessarily this subgroup is normal. If we want to build a normal subgroup with the same property, we can work harder. Well, in abelian case, all the subgroups are normal. Well, finite subgroup H subset G such that B subset is a subset of coset of H, of some coset of H. A is union of cosets of H. This is equivalent to this one. Well, proof. This requires only basics of group theory, so you don't need to know more than Lagrange theorem about subgroups, right? That cosets are non-intersecting, different cosets non-intersecting, right? When they are two cosets are equals, are the same, or non-intersecting, right? Look, well, suppose we have the structure. A is subset of subgroup, so B is subset of X plus H. Yeah, this is coset. A is union of cosets. A is union of cosets. It's union of from I from 0 till I don't know m minus 1 y I plus h. How to show that A plus B, size A plus B, is coordinate of A? How to show it? Well, A plus B is what? The union of what? Why? Because easy to show this inclusion A plus B is contained inside here, but how to show the opposite inclusion? Sorry? Yeah, well, from this follows this inclusion. We have to show this. Yeah. How to show this inclusion? Contrary one. Look, what cosets we get when we add any element from B to here, to A. Just let's choose any element from B and add this element to A. What is gets? What cosets we get? Right? B plus A equals to what? But H small plus H is H, right? H small plus H is H because of the main property of subgroup. If we add any element, add two elements from subgroup, we get elements from some group, right? So for any element B, when we add this to A, we get the same set. So this shows that we cannot get more than, well, we get, but when, even if we add one element, we get the whole union. So we cannot get more. So opposite inclusions shows that this is B plus A is subset of A plus B, but this is equals to this union. So these sets are equal, but size of this set is size of A, because we shifted all the cosets by one element, all the cosets. So we didn't change the size of set, we changed all the position of the set, right? Come on, guys. Okay. Well. Direct statement. We know that A plus B has size A. This is all we know. We have to prove that we have to find this subgroup and prove that we have this structure. Okay. First, find the subgroup. This subgroup is this one. All the H from G with property H plus A is A. Why this is subgroup? Symmetry subgroup. Why this is subgroup? How to check that something is subgroup? Zero belongs to H, naturally. Zero belongs to subgroup, first. Second, if we take any element from subgroup, then some of these elements also inside the subgroup. How to show that? Right? A third, if H is in subgroup, then minus H is also in the subgroup. How to show that? Right? You see, in the construction of the subgroup, we don't use commutative property, commutativity. We don't use commutativity here. But, well, the main problem in non-commutative case here, that this subgroup could be not normal. It's bad. Well, What next? First, prove that, just select any element from B. Choose any B0 from B. Five minutes, yeah. Choose any elements from B and consider B1, it's B minus B0. Well, what can we say? We can say that B1 plus A contains 0. Well, and also we can say that B1 plus A has the same cardinality as A plus B. Right? We also can say that A is contained inside A plus B1, right? And since B1 plus A has cardinality A and A contained inside B1, this means that A equals to A plus B1, right? Not cardinality of A equals to cardinality of A plus B. A equals as set as to A plus B1. Right. Second, A is union of cosets. Oh, this means that B1 is subset of H. By definition, right? So B1 subset of H. H is all the elements with this property, such that H plus A is A. So we add B1, we didn't change A. So B1 subset of H, and this means B subset of B0 plus H. The first part is proved, B subset of cosets. How to show that A is union of cosets? Well, this is main property for, we won't use even this. We don't need to, we don't need it. When we define the symmetry subgroup, this appears automatically. The A always union of cosets of its symmetry subgroup. Okay, we finish this, and well, when we finish prove this theorem, we finish the lecture. Okay. Suppose coset has non-empty intersection with A, any coset, X plus H has non-empty intersection with A. We're going to show that any coset of subgroup H either contained inside A or not intersecting with A. Right. Suppose we have non-empty intersection. We have to show that X plus H is contained inside A. How to show that? Then there are A from A, and there are H from H, such that A equals X plus H. Good. A plus H is subset of A, right? But it's the same as X plus H. Well, okay, so X plus H, but this is H. So this is X plus H. So we showed that X plus H is subset of A. So if the coset has non-intersection with A, then it contained inside A. That means that A is union of cosets, right? That's all. Okay, let's finish today's lecture.